Hello everyone, thank you for having me in SDC 2021. My name is Jung-Soo Kim from Samsung Electronics and I'm taking charge of developing SSD reference system called Poseidon. Today I'd like to talk about the characteristic of EDSFF and its applications. Moreover, I'd like to share the I/O performance of E1.S SSD reference system that we introduced last year. And my colleague, Doug Ho, is going to present about the NVMe-oF fabric solution called Poseidon OS. I won't talk too much about the details of EDSFF because it's been introduced quite a lot in the industry. Instead, I will go over the high-level characteristics and its applications. EDSFF stands for Enterprise and Data Center Standard Form Factor. When the EDSFF was first introduced, it was SSD form factor, not Enterprise form factor. But it was changed from the SSD to standard form factor due to the many advantages. For example, it is designed to overcome the conventional device limitations. It improved power and thermal characteristics and supports high-speed interface and so on. Also, EDSFF allows customizable latch and extension key design. EDSFF is designed for overcome conventional form factor limitations. M.2 form factor was developed for client use and mostly used as a boot drive in data center systems. It has limited performance, power, and scalability, and most of all, doesn't support hot plug. U.2 form factor was developed from 2.5-inch hard disk drive form factor. Even though it is currently the most popular form factor in the industry, it still has power limitations and disadvantages for high-speed interface like PCIe Gen5 or higher. There are 5 different kinds of form factors in EDSFF E1. E1 short has 5 different thicknesses, and E1 long has 2 different thicknesses. As you can see on the table, as the thickness is getting thicker, the power capacity is getting bigger. And as the thickness is getting thinner, the system density gets higher. The power consumption of single PCIe Gen4 E1.S SSD is less than 13 watts. So for our reference system, we chose 9.5mm E1.S SSD for our reference system. Because the system was designed for the old-fashioned storage, and the 9.5mm SSD offered the highest density, while satisfy the power and thermal requirements. EDSFF E3 form factor design is optimized for 2U system. It has 2 different kinds of thicknesses and lengths. The advantage of E3 form factor is that it can use higher power and supports various interfaces. Let's look more of the reasons in the next slide. First of all, E3 offers a variety of power options from 25 watts to 70 watts, which means it can accommodate not only the SSD devices, but higher power devices like AI accelerator or network interface card. Second, it supports various PCI bandwidths from by 4 to by 16. According to your application, you can choose the interface bandwidth accordingly. Third, EDSFF enables better signal integrity of the device. If you look at the right bottom of the slide, U.2 device has 2 connectors, 8639 receptacle and plug, while EDSFF device has only 1 connector in the backplane side. The new design allows better SI, and it enables the EDSFF device high-speed interface over PCIe Gen5. Because of its robustness of EDSFF, we can develop various new applications. From now on, I'd like to introduce E1.S SSD toolist design and device management control (DMC) that utilizes EDSFF E1 and E3 devices. After we announced Poseidon system last year, we received various feedbacks from industry and customers. One of the feedbacks from data center customer was that we wanted to remove the screws from E1.S SSD so that they don't need to use the tools in their data center. So we started to develop the toolist SSD design with our ODM partner Inspur. As you can see in the slide, we came up with a clip type design, and above all, the SSD enclosure is compatible with current screw type extension kit. Let's look at the real demo video. As you can see, the toolist type is 10 times faster than current screw type. It only takes 4 seconds to assemble and disassemble the extension kit from the SSD. If a data center has millions of drives, you can save 100,000 hours. It is same with the system vendors. We are going to open our toolist design to OCP community, and we want to discuss and improve the design with the industry. Please give us good feedbacks, and we want to work with you to improve our new design concept. DMC, device management control, allows the system to collect hardware information of the device while the device is failed. Current device uses processing unit, which is called controller, to collect and send the hardware information to BMC in the motherboard. However, by replacing the EEPROM with the management control unit on the right side, the MCU collects hardware information instead of processing unit, and the MCU is connected to BMC. With a new device, a system can collect and monitor device status in any time. We started this project with customer needs and collaborating with system vendors to develop the BMC and DMC devices. We are developing the device as a E3.S2T form factor to target high-speed PCIe Gen5 NVMe SSD. EDSFF is so flexible and powerful. The new form factor allows us various new applications of the device and system. Now let's talk about the EDSFF E1.S reference system Poseidon V1 server that we announced last year. If you compare the U.2 based system with EDSFF based system, the benefits of EDSFF is very clear. When you optimize E1.S system, can increase the density dramatically. As you can see, traditional U.2 1U system can accommodate 10 SSD devices, while E1.S SSD can accommodate 32 SSD drives. With E3 devices, you can not only increase the SSD density, but also transform the system for various applications. For example, if you want to increase the DRAM capacity, you could utilize CXL memory expander, while if you want to offer CPU resources, you can utilize Smart SSD in the same platform. Since the EDSFF E3 is so flexible, you can transform your system according to your needs. We introduced the project Poseidon last year. The Poseidon Project is an open source based multi-industry collaboration program. Component vendor, system vendor, and data center got together to develop next gen storage system, which is Poseidon V1. Now the V1 E1.S reference system is officially launched and being tested at the data center. Today, I'd like to share the system architecture briefly again, and we want to share our system test data. The Poseidon system is the latest EDSFF E1.S SSD reference system optimized for NVMe Fabric target node. It is a 1U height PCIe Gen4-based Ice Lake 2-socket system and utilizes latest Samsung PM983 SSDs. Samsung PM983 SSD supports 4 lanes of PCIe Gen4 and delivers up to 6 GB of I/O performance. To be optimized for a shared network storage node, the Poseidon system comes with a total 32 NVMe SSD and delivering up to 256 TB of capacity. It also provides up to 400 gigabit Ethernet of network bandwidth with RDMA capability to deliver the high bandwidth and low latency I/O. The system diagram shows the PCI topology of Poseidon system. Since Poseidon OS recognizes the NUM architecture, the topology is designed symmetrically to minimize the latency and offer stable I/O. Obviously, PCI bandwidth for network interface limits the total bandwidth of the system. However, we assign the full PCI lanes to every single SSD and use the PCI switches to improve the I/O performance. This slide shows the read and write performance of the single and aggregated SSDs. The reference system utilizes for Samsung PM983 4TB SSDs. On the upper side of the graph shows the EC32 single SSD read and write performance. We could see that the uniform bandwidth and latency on all SSDs as we expected. On the bottom graph shows the aggregated read and write bandwidth of the system. As you can see, local aggregated write bandwidth is about 96 GB per sec, and read bandwidth was more than 100 GB per sec. And the stair-shaped graph shows that our system operates as we designed. From now on, my colleague Doko will present about the Poseidon OS. Thank you.
Hi, I'm Doko Bae, and I'm taking charge of developing NVMe Fabric reference system in Samsung Electronics. Today, I'd like to talk about open source software solution for NVMe Fabric called Poseidon OS, which is highly optimized for EDSFF-based server. Firstly, I'd like to introduce NVMe Fabric interface briefly. NVMe Fabric interface has emerged to break through the scaling limitations of PCI attached NVMe, which is limited to scale only a few hundred of drives. To overcome this limitation, NVMe Fabric uses a transport protocol over a network to access remote NVMe drives. Through encapsulation and decapsulation, NVMe Fabric can maintain end-to-end NVMe semantics across a range of topologies. In this figure, NVMe command from host side is encapsulated and is sent to storage server via network protocol. When the command is reached to storage server, it is decapsulated to NVMe command and is issued to local NVMe drive in storage server. Since NVMe Fabric interface eliminates unnecessary protocol translations, it can retain NVMe efficiency and performance over network fabrics. So, why do we need NVMe Fabric system? Modern data center storage system architecture is evolving toward the disaggregated architecture. With traditional directed attached storage architecture, you will need many SSDs and CPUs to run a huge amount of storage pools. However, by decoupling storage from compute, you can reduce the complexity and increase performance and efficiency of infrastructure. And the flexibility of infrastructure will increase. You can dynamically allocate compute and storage resources of shared storage pool. NVMe Fabric is a standard network storage protocol to enable such disaggregation storage pool. Before sharing the details of Poseidon OS, I'd like to talk the vital virtues for NVMe Fabric solution. This helps in understanding the concept and design of our solution. These are 4 vital virtues we think. Firstly, NVMe Fabric solution should provide ultimate and stable performance, since it is natively for sharing storage resources. More performance can allow more connections to share. Second one is, it should be high available. High availability is essential for storage system, but this becomes more important in EDSFF system. With high-density EDSFF SSDs, we can easily achieve petabyte scale capacity in a single server. So we need to more considerations about high availability for NVMe Fabric system, especially for EDSFF SSDs. Next one is, in order to provide valuable storage features at petabyte scale, it is important to manage internal metadata with low performance and space overheads. The next and last one for NVMe Fabric solution is, to meet all above vital virtues, it should utilize all resources in the system, including CPU, memory, and network, in an optimized way. Let me move to Poseidon OS. As you can see in this figure, Poseidon OS runs as user application on Linux kernel, and it can provide volumes to the initiators via NVMe Fabric, which are shown as virtual block devices in the initiator side. Since Poseidon system is co-designed both hardware and software, it can meet all vital virtues mentioned in the previous slide. It can provide PCIe Gen4 performance with up to 200 GB Ethernet network and support the following valuable storage features for shared storage system. And Poseidon system is kind of a storage building block for disaggregation architecture. It provides integration APIs for easily integrating with upper orchestration layer like Ceph or Kubernetes. Let me explain about a storage hierarchy in Poseidon OS. As shown in this figure, Poseidon OS has low-layer hierarchies such as memory, NVDIMM, and NVMe SSDs from top to bottom. Since Poseidon server has 2-socket CPUs, you can see that all storage resources are managed separately based on their NUMA nodes. This allows to minimize UPI transactions and spend more CPU cycles for storage services. In the memory layer, Poseidon OS stores its metadata just like other systems. And in the NVDIMM layer, you can see the write buffer and journal buffer. Write buffer is for shortening write latency and making SSD friendly writes. And journal buffer is for protecting user data in case of sudden power off. Since all user writes are first stored in write buffer occurs flush operation to NVMe SSDs, and journal buffer is required periodic checkpointing operations. If you look at the NVMe SSD layer, you can see that Poseidon OS creates RAID group called array from multiple NVMe SSDs on a single NUMA node. Array is accessed in smaller unit. A smallest unit is a block, which represents an I/O unit from the client, and normally has 4 kilobyte size. And a chunk consists of multiple blocks, and its size is determined by the size that can obtain the maximum write performance of NVMe SSD, which are equipped in Poseidon system. Poseidonos issues write commands only in chunk size, and by doing so, it can fully exploit write performance of each NVMe SSD. And a stripe is an allocation unit inside Poseidonos and to store user data, and its size is proportional to chunk size and number of SSDs. And the segment. Thanks to write buffer, Poseidonos stores user data in low structured manner, so it is necessary to system-level garbage collection, and thus the segment is aligned with garbage collection unit of NVMe SSDs equipped in Poseidon system. Let me explain software rate of Poseidon OS. Since EDSFF can provide ultra-high capacity up to 128 terabytes in a single drive, it is necessary to provide fault tolerance method when NVMe drive fails. Since hardware-led card for NVMe SSDs does not become popular yet, so software RAID or erase coding can be a good candidate. We choose low structure RAID approach because we store the user data to SSDs in low structured manner. Low structure RAID follows naturally. The brief life sequence of low structure RAID shown in this figure. As I mentioned before, all user writes are first stored in write buffer, and write parity is only calculated when write buffer is full, and then flush them with user data in low structured manner. This can reduce WAF and QoS impact for user IOs. Let's move on the performance evaluation. We used Poseidon server equipped with 32 PCIe Gen4 SSDs in total. And the server is connected with two initiators via NVMe TCP protocol at 100 gigabit Ethernet speed respectively. For Poseidonos, we created two numer-aware arrays, which of each consists of 15 data drives and one spare drive. To measure maximum performance of Poseidon system, we created 43 volumes in total. And we used user space driver in the initiator side, which can boost the write performance. This figure shows maximum performance of Poseidon system in case of sequential read, sequential write, random read, and random write respectively. You can see that a single Poseidon system can achieve up to 200 gigabit Ethernet performance via NVMe TCP in most of cases. Especially, the performance of sequential read is up to 24.5 gigabyte per second, which is saturated by network speed. But in case of random writes, CPU for TCP stack becomes a main bottleneck, and there's plenty room to improve. In fact, we had same problem in PCIe Gen3 system, but in PCIe Gen4 system, which doubles up the performance of SSD and network, it would be much worse. So you can expect more randomized performance with adapting RDMA or SmartNIC, which can eliminate or offer NVMe TCP offload functionality. I'd like to move on next result. According to our observation, Initiator software stack doesn't matter to fully exploit embedded fabric performance. This graph shows that the relative performance between user space driver and kernel driver in the Initiator side. Fortunately, in case of sequential read, both user space and kernel drives can be achieved max performance. But except for that, kernel drive has up to 23% performance drop. This gives us an insight that in order to fully exploit embedded fabric performance, it is important to consider the Initiator side software stack as well. The last result is about I/O consistency of Poseidon system. For this, we did long-term I/O with mixed workloads. In this figure, you can see that Poseidon system provides very stable QoS. Thanks to user space inheritance and two-stage I/O paths. As time goes, the I/O consistency slightly drops due to internal I/O triggered by both system level and SSD level garbage collections. Finally, I'd like to share our future workflows of the solution. We are considering that support more innovative NVMe drives like Gen6 in Poseidonos, and more storage features will be supported. Also, we have planned to provide developer toolkits. Since our project is based on open source, many collaborations from outside are of great help. To promote this, we will provide useful toolkits for developers, such as performance provider, dev APIs, and so on. Finally, we will move to PCIe Gen5 to leverage its environments. For this, we will migrate Poseidonos to PCIe Gen5 when the server is ready. Poseidonos is available at GitHub, so you can get more information about Poseidonos in the GitHub. Thank you for watching our presentation. We are more than happy to receive any feedbacks from you. If you have any questions, please feel free to contact us. Thank you very much.